In this short video, we're going to talk a little bit more about countable sets. And notice I put a star up here and some asterisks. This is a very important statement. Suppose that the function f going from a set S into the natural numbers is 1 to 1. Since the natural numbers is a countable set, and f of S, the image of S, under the function f. So that's all the numbers in N that get mapped to. It's got to be a subset of the natural numbers. Well, that means that the f of S is also a countable set. So, the moral of the story is, to show that a set S is countable, it suffices, or it is sufficient to find a one-to-one function from S into the natural numbers. It does not have to be onto. This is much easier. And technically, I could replace this natural numbers with a set of integers or any countable set. Because remember, we already proved that there's a one-to-one and onto function between N and Z, the integers. That would have made our lives easier on an earlier example when we were mapping the even natural numbers into the set of natural numbers. We were trying to make sure it was an onto function. We no longer have to do that. We could have just said, let f of n equal n for every element in the set of even integers. And it would have been a one-to-one function. Even natural numbers. It would have been a one-to-one function. It's not required that we make it an onto function. Theorem 0.16 is a powerful theorem, and it's a basis for many other theorems. If two sets A and B are both countable, then the Cartesian product of both of them is also countable. Remember what the Cartesian product is. It's a set of all ordered pairs, where the first element comes from capital A and the second comes from capital B. Let's do since the proof is short, let's go ahead and do that right here. I think I have enough room. I might write a little bit smaller. Let's let f be a function mapping A into N, and G be a function mapping B into N. And furthermore, we can require that they be one-to-one functions, that f and g be one-to-one functions. And why are we allowed to do that? Why do we know such functions exist? Because A and B are countable. It's a definition of being a countable set. Here is an interesting part. Let this new function h that takes as an input, actually I don't need the parentheses there. I don't need two sets of parentheses. I'm defining this to be 2 to the f of A times 3 times g of B. Let's think about that function for a minute. I want to take every ordered pair, A comma B, where A comes from this set and little b comes from that set, and map it to a unique natural number. By unique, I mean where no other ordered pair will map to that number. I need it to be a one-to-one function. Well, why is that a one-to-one function? Maybe I will write a statement down and then I'll explain it a little bit more. Since f and g are one-to-one functions, so is h. And I'm going to put by the, for one reason, I'll put by the unique factorization theorem. You remember the unique factorization theorem. Maybe you don't remember it by name, but take a natural number, 10. It has a unique prime factorization. You know, if you were going to put the factors in order, say in increasing order, 10 would be 2 times 5. Let me use 20. It would be 2 squared times 5. It has a unique factorization. No other number has that. So what we're mapping these to is 2 to the f of a. 2 and 3, because they're prime numbers, we can guarantee that AB, every AB pair gets mapped to a unique number. There's no other pair that's going to give the same factored form like this, 2 to a power times 3 to a power. This is a one-to-one function. That's a one-to-one function. This is a one-to-one function. You may want to think about that one for a little bit, but just as I could have picked 2 prime numbers here, other than 2 and 3. I could have picked 5 and 7. 5 raised to the f of a times 7 raised to that, and it would still be a true statement. Okay, so we have h being a one-to-one function, and we're done. That means, therefore, A cross B is countable. That's the end of the proof. We found a function that maps A cross B into, not onto, but into the integers. And we're done.